Before we start introducing the roadmap of constructing models for the bridge controller, I would like to actually clarify a very crucial concept which will be applicable to every case study that we're going to do throughout the course, which is called a state space of a model. And I can tell you the take-home lesson right away, which I'm going to conclude ultimately for this part of the lecture. The state space in some way actually quantify about how large the scope it is for you to verify the correctness of your system. So if you talk about the source code, the state space is simply too large for you to really even consider. So that's why verification on the source code is simply not practical and infeasible. And for the case of a model, depending on how you actually choose the variables or constant and their constraints, how you specify them in your model. In that case, in many cases, it would be feasible to really consider. And of course, if you choose the variables and constants in such a way that the resulting state space is way too large for you to really consider, that's also not acceptable, right? So that's kind of the balance you will have to strike as a modeler, as an engineer. Let's now just move on to talk about the definition, and I'll give you just some example just for you to get a feel about how to approximate the state space of a model. So you will always keep that in mind whenever you construct your own model. A model's state space is simply the set of all configurations. So whenever you want to see how large the state space is, you want to think about what is really the cardinality of this particular set. And each member in the set is basically we call a configuration. And each configuration assigns values to constants and variables subject to, let me go over the definition and I'll give you an example. Axiom and also invariance. So whenever you actually declare constants and variables, as we learned in your rodent introductory tutorial, you will have to specify the associated typing constraints about what the type is for the constant or for the variable. Maybe the constant is simply an integer, or maybe the variable's typing constraint says that it should be a partial function, and etc. So these constraints, together with the types of the variables, all the variables and constant declared in your model, they will determine how large the state space is. And before I move on, let me make one more remark about the state space. You should always remember the state space is really the set of all possible configurations, and each configuration is a particular instantiation of all the constant and variables, which means your system might actually reach that particular state. So whenever we want to prove a property about a system, you want to make sure that property can hold on all the possible configurations of your state space, right? It's really a universal quantification, not just existential. We want to make sure that all the possible states that a system might reach, they can satisfy all the desired properties rather than just a single one, right? That's very important. And if there's any, remember how we disprove universal quantification. If there's any particular configuration of your states that will violate the desired property, for example, in that case, in the case of rodent, you just cannot prove the theorem. And in other tool, something called model checker, in that case, it will simply give you a counter example. But for model checker, like a model checking subject, we don't really cover in this particular course. We focus more on the theorem proving side. But for model checking, we'll do that in your safety critical system course in the 4th year, right? That's something you can look forward to later. All right, let me move on. And let's now talk about one example over here. Let me just switch to my iPad and make all the points I would like to convey over here. Right, so we talk about the state space of a model, right? And let's revisit the definition. The state space of a model over here, the state space of a model is simply the set of all the possible valuations or configurations. So these two terms people actually use to mean the same thing, just different instantiations of the constants and also variables, subject to declared constraints. And the constraint may be for typing or maybe for desired properties, right? Just remember. But constraint is a very general term that may be meant for different purposes. It could be for typing, or maybe can be for desired properties. Right? In the case of a typing, it will be something we assume, so we declare it as axioms. But in the case of the property, that's something we would like to prove as theorems, right? That's something we actually cover in the rodent tutorial. Theorems, and also here for typing, it will be axiom. So these are just two examples. Right? Let's now consider one example model over here. let's say we are trying to formalize or create models for a bank system. What we start with is the so-called initial model, the very first one. It simply is declared with two constants, C and also L. So C for the credit limits and also L for the upper limits for every account, right? And also a variable. Let's say the variable is simply just called accounts over here. Account is a member of the set of functions over here, partial functions specifically. So it's a partial function from ID into a string ID into the balance of that particular account. And the reason that it's actually partial function is because not necessarily every string will be a valid account ID in the current bank, right? That's a justification that we did also in the lecture for other examples, right? So here, the first line over here in green, so these are simply the typing constraint. And just remember N1 over here, we didn't really say that in the lecture in the math review, but we said that in the tutorial. So N1 over here is simply all the positive number, okay? So that will be, let me just say positive number, right? The set of all positive numbers. It's more like a superset of just N, which will start with 0. Right, let's take a look at the desired property over here. We say for every ID, like a string, and ID is a member of the domain of the accounts, which will be the string over here. We're saying that ID is such string that will be in the domain of the accounts, like a valid account ID. It will be the case that the ID of the balance of that particular account ID, right, is going to be in between these particular limits. It should not be more than the maximum limits on the account balance, and also it should be larger than or equal to the credit limits. For example, if the credit limit is 300, in that case, your account balance should be larger than or equal to minus 300, right? That's kind of the concept we already did. We already practiced in the lab. All right, so we got typing constraint, we got desired property, right? So now here we got two questions to really work through for us. Number one, you can definitely do maybe by pausing the video and think about. So I want you to give, actually should not be given, should be just give, right? Let me fix that very quickly. I want you to give some example configurations of this initial model's state space, right? So what I want is not just about to enumerate all the possible configuration. What I want you to do is give me some example. Right? You can now pause the video and think about it. All right, assuming that you thought about it, let me give you two examples, right? Kind of corresponding to what you will see in the slides. Okay, so example number one. Okay, example number one. So we have to instantiate, or we have to give the valuation of the two constants and also the one variable, right? So let me just put it as a 3 tuple, okay? So what about the credit limits? The credit limit can be any positive number. So let me say C will be, what about, let's say 3,000, okay? So that means any account in the bank cannot go below minus 3,000, okay? And we also need to give a valuation for the upper limits, like what's the maximum balance each account can have. Well, we can make it maybe, I don't know, let's say it's going to be universal for all the accounts. Let's say L will be, let's say 150,000, let's say. Right? And then we also need to give some valuation for this accounts over here, which is a partial function, right? And well, remember, empty set is simply a partial function. Agree? It definitely is a valid configuration. So this is one possible configuration. Of course, if you want to make a note, this particular one here simply denotes an empty bank. Right? That's example one. And example one over here, we have to make sure this empty relation will actually satisfy this cover. Indeed, it will satisfy, because you just cannot find any witness that will violate it. Right? That's example number one. Let's give another example where the bank is not empty. All right. So we can do example number two. And for example number two, let's say we have maybe a slightly different credit limits, right? Because it can be any positive number for credit limits. Let's say 3,500, right? And also L will be, let's say 200,000, let's say higher. And what about the actual bank? I mean the accounts. In that case, oh sorry, here I should really say accounts is equal to, right? That's what I meant to say. So now we can say accounts is going to be a enumeration of some partial function between string ID and also the integer balance, right? Let me just give you a bank with only 2 accounts inside. So what about the ID? Well, just symbolically, let's say ID1, right? It can be any valid character sequence that will make a valid bank ID. ID1, that will be the domain value. And what about the integer value? The integer value should be larger than or equal to minus 3,500. And it should be less than or equal to 200,000. Well, otherwise you wouldn't satisfy this constraint. So I can simply put, how about just 150, right? That's definitely valid. And also let's say we got another ID, another account with ID 2. And maybe that one, maybe 1750, right? You can kind of see what I'm doing here. The way I'm doing here is to simply work out combination of the constant, the 2 constant, and also the variable over here, such that it will satisfy all the constraints we have already specified. So that will determine the model's space, right? And you can think about this is a member of the state space. This is just another member of the state space. That's also very important to actually see. Okay, so you can think about this is a member of the state space of this particular initial model. And similarly, this is also a valid member of the state space. Hopefully, so far so good, right? It's really important for you to at least to come up with some example valid valuation or configuration that will be members of the state space. Right? Question number 2 is the concluding question, really. So now, given that you know how to find out individual examples, how large exactly is this initial model's state space? That's the question. All right, you can pause the video and think about it. All right, hopefully you didn't really think too hard, right? Maybe, well, if your intuition is very big, almost like an infinity. Well, not exactly infinity, because everything over here in some way is still finite. Maybe at least countably infinite. At least we can count. But let me just not really go there to be too mathematical. But let me simply give you some idea, right? It's something. Whenever you are asking about how large exactly is the state space, right? So there is a term which I also mentioned in the slide. It's a combinatorial explosion. Combinatorial explosion. Think about choosing different value. How many possible values? So here we got 1, 2, and 3. 3 model components over here. 2 constants and 1 variable. And if you really want to make a valid valuation or configuration of the model, you actually have to consider their type over here. So how many possible values can you choose for C? Well, since it's all positive, right? It's basically any value that will be starting from 1 all the way to infinity, right? Theoretically speaking. And also over here, this will be also any value that's going to be positive. And this one over here will be basically any function that will actually satisfy this particular constraint, being partial between the string and also the integer, right? And of course, not necessarily all the combination for between all these 3 will be valid. You still have to make sure all of them together will actually satisfy this particular property, right? So for example, if I just give you one example, what would be one example where it should not be a valid configuration? Okay, so let's say invalid configuration. That's also important, which I'm glad I remember that I will mention, or valuation. Okay, let me give you one example exactly over here. Let's say C is equal to, let's say 4,000. L is equal to, let's say 175,000. So far so good, right? You can see this is a positive number, and this is also positive number. And what I will do here is I'm going to make just a non-empty bank with just one account. Okay, just to illustrate why this might be invalid. Let's say over here we're going to get, let's say ID1 over here, and then the balance, right? Let me say it's minus 4,500 over here, right? This will be very important for you to see, okay? Definitely, this is a valid member from the set over here. This is a valid member from this set over here, and also this is a valid member from this set. It's simply just a partial function automatically by definition. You can definitely refer to the review lecture on math. However, this particular valuation does not satisfy this universal quantification as the desired property, because exactly over here, you can see for this one here, right? In order to disprove universal quantification, you need a witness. So this will be the witness that violates this property over here, because you can see the balance over here is not larger than or equal to minus 4,000. It's not. So this is actually smaller than that, right? That's something you want to be very careful and understand how, right? You can think about this is a witness of violating exactly this property over here. All right, so not necessarily every configuration you can come up with is a valid one. You want to make sure not only that it satisfies the typing constraint over here, but also you should satisfy the desired property. But leave that aside. How large roughly should it be? Well, since I talk about this, so the fact that we call it a combinatorial explosion, so that means you have to somehow multiply the cardinality of the domain the size of each variable type or constant type. So in this case, it's going to be the cardinality of the type of C, which will be this, multiply also the cardinality of this, which will be L, and also the cardinality of this particular type, string, and also partial function, and this. Right? Of course, it could be smaller than this, strictly smaller, because not necessarily all the possible combinations would be like a valid valuation as I explained, but it will be fairly close. All right? Well, apparently, this is actually infinity. You can definitely say that. It's already infinite. All right? It's I spelled it wrong. Right? If it is really infinite, so that, what does that mean? Okay, that means several things over here. Let me talk about it. Right, this one is not really remarked in the slide, but I think you definitely should really understand this. Number one, it would be infeasible to test all possible values of the model. So here, when I say test, like for example, you can write a JUnit test cases, right, for a particular input or like a particular every JUnit test can only capture certain valuation or certain configuration of the bank. You have to make it concrete. So it's simply infeasible because you have to write an infinite number of test cases in theory. So that's not possible, right? Of course, if you took maybe some 4th year level software engineering testing course, they would say, admitting that we have combinatorial explosion for your model or source code, you have to make some good judgment about covering some equivalent classes, so-called. But I'm not going to cover that in this course, right? Just want to mention that it's infeasible to really test all the possible input value just because the inherent combinatorial explosion problem, even for simple model like this, even for. All right? And point number two. Point number two, in the case of a theorem proving approach, which we adopt in this course, theorem proving can address this effectively. So what does that mean? If you recall what you did in lab number 1, we did actually theorem proving in the rodent tool, right? Let me highlight first of all theorem proving, and this is what we did. We actually created one context and one machine. The context declared two constants, and also constant like this, and also the machine declare variable like this, and also we got the associated invariance or axiom, things like that. And then we were able to see that the automatically generated proof obligations by the rodent tool was able to be discharged automatically without our intervention, right? Sometimes you may have to put in some manual proof, but in the case of lab 1, the theorem prover were able to discharge the proof obligation without our guide, right? So what does it really mean? When we saw that smiley green face in the rodent tool, when they said all the proof obligations generated based on the declared constant variables and constraints are discharged, what does it really mean? So that means the prover managed to really manipulate the typing constraints and also the invariance. They're all predicates. They were able to manipulate these at the abstract level, and they were able to prove them rather than testing the concrete values, like using the concrete value like what you have to really supply in the case of a JUnit test cases, right? Let me write it down. I think that's something also very important to really highlight, right? So now maybe let me put it here, right? Let me try not to cross any line over here. Okay, let's now talk about it. So in the case of theorem proving, so that means the theorem prover under behind the scene, they try to manipulate symbols at the abstract level. Manipulations of symbols and predicates, right? For example, you can see this is of course predicate propositions. You can see this is a proposition, this is a proposition, this is a proposition, and this is a predicate. They kind of try to combine everything together and try to manipulate it in at an abstract level and try to prove that it's actually a theorem. Of course, exactly how things are done, we don't really have to know, but we'll get a feel when we try to do some manual proof ourselves, when we talk about inference rule of the sequence calculus later in this lecture. All right? All right, so here, manipulate at the abstract level. Right? It's really important to see that these are all the stuff that we talk about in the math review lecture, but now they actually put into some tool in practice. Okay, and so you want to really contrast this with concrete values, concrete valuations for individual JUnits tests. If you simply just want to prove the theorem by testing as many valuations or configuration as possible in your JUnit test cases, in theory, you can never be complete because the combinatorial explosion. But if you try to prove things at the abstract level based on inference rules, like proof rules, in terms of the predicate and proposition, that's actually possible to really argue in a universal way. All right, let me recap very quickly. So whenever we talk about the state space of the model, you should really know about the answer to Q1 and Q2, just have an idea. And because of the combinatorial explosion, we have to really appreciate that we can do some theorem proving, even though proving itself is a very creative and hard process, but at least you can address the combinatorial explosion pretty well. So whenever, for example, if we are able to prove, let's say this particular theorem, if we are able to prove it, so effectively, what we have really proved is for all the possible combination for the accounts and also C and L, we are doing a universal quantification proof. If we can prove it, so that means is effectively testing all the possible values, which simply cannot be done in practice, right, by JUnit test cases. All right, that's quite a bit of a discussion over here, but I thought that's really important for you to understand about state space before we move on to construct our first model. All right, let me come back here, and the rest of the slide has been discussed already, right? Combinatorial explosion over here, and this will be some little formula you want to keep in mind. The more concrete you make your model, meaning that the more variables and implementation detail you introduce into your model, the most concrete model will be your source code, right? In that case, it will be a very large state space, and also verification difficulty will be simply grow exponentially. Even for theorem proving, it would be quite difficult to really still to complete if your state space is excessively large. That's something we would discuss as well, right? But that's kind of the formula I want to keep in mind. And a model's complexity should be guided by those properties that you intend to really verify against the model. So you want to think about all the requirements I would like to prove as correct. Eventually, I want to distribute those properties into a series of models. So one will be refinements of another. In that case, we can kind of put some manageable amounts of details to be verified in a particular model, right? So that'll be the final 2 points I want to mention. It would be infeasible to try to prove all the desired properties on the model, in which case your state space will be way too large to really even to prove. Number 2, it would be feasible if you can distribute the desired properties over a list of refinements, which is something we'll see for the bridge controller. All right, and starting from the next part, we're going to talk about the roadmap of how we're going to construct models for our bridge controller.